Welcome back. We're looking at the advantages and pitfalls of different methods, and the method we're currently looking at is the integer chip method. So we have all 5 questions already placed up on the board, and we'll just jump in and start right away. So I'm going to be using the concept of 0 pairs being an X, which is my negative, and an O being my positive. Again, students will have been introduced to this concept of 0 pairs. Teachers would have taken time explaining that when you have 1 candy and you take away a candy, you have 0 candies. So then a 0 pair would be equal to 0. Make sure that looks like a 0. So that equals 0. They'll get that concept that this equals 0, and that any number plus 0 is still the same number. And this is sort of me recapping this very quickly, but you would have spent quite a significant process on this concept. So students could be comfortable with the fact that I could have added as many zeros as I wanted. It wouldn't have changed my value of 9. So when working with integer chips, students know that they can have, let's say they needed to have 4 integer chips. They could have just 4 little circles, or they could have 4 little circles and as many 0 pairs as they want, because that's 4 plus 0 plus 0 plus 0 plus 0. So ultimately, it's still 4. Okay, so that's a little side note there. Let's just get rid of that so we have some space to work. Let's see if we can erase that whole thing. Should be able to let me, nope. All right, so working with the first question, we don't even need to worry about negatives. So let's start by the first question. So the question is 24 take away 16. So I have 24 positives, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's 20. 1, 22, 23, 24. And students would probably count that way. They probably wouldn't be able to group in groups of 10. They'd just draw 24 dots, depending on what age, obviously. The older they are, the more they can sort of group it. And I'm taking away 16. So I know I have to take away a full 10 grouping. So all these are gone. And again, I can, in older grades, they can just know that that's a 10 grouping and they'll take the whole grouping away. Younger kids will have to count 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 and take those 10 away. They might just continue counting and say, 11, 12, 13, 14, 15, 16, and then count their answer 1, 2, 3, 4, 5, 6, 7, 8. Again, so once kids get older, they'll be able to just sort of break it down. They'll scrap the 10 right away. They'll scrap this top, let's say 6, and then they can visually see that there's 8 left. But that's sort of an age-related thing, and also just how you visualize numbers and how they speak to you. So let's look at number 2. So number 2, we're starting with 16 and we're taking away 24. So again, I have to draw my 16 that I'm starting with. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6. And I have to take away 24. So I don't have 24 to take away right away. So we tell students, they'll say, oh no, I can't do this. And we say, remember what I said. Remember about 0 pairs. I can write 16 like this, but I can also write 16 like this, and I can keep adding zeros, as many zeros as I wish. And once they realize that, they'll keep adding zeros until they need them. So I know I've taken away 24, or I need to take away 24, so I take away the 10. So now I have 14 left to take away. And I can take away the 4 right away. So now I have 10 left to take away. I can take away the 2, so I have 8 left to take away. So I take away 8 positives, only positives. 1, 2, 3, 4, 5, 6, 7, 8. So those zeros stay as zeros. I don't have to worry about them. So I count my negatives that are left over. 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 negatives left over. So those are not positive, so I need my negative sign. Those are 8 negatives left over. So this method works for number 2. Let's look at number 3. Number 3, I have 740. Oopala. Sorry about that. I'm writing up in the sky here. For number 3, I have 748 minus 54. Well, integer chips would work. It would take forever. So based on that, I would say they don't work. You might be able to support it visually without integer chips. You could use tiles. So I could have 700ths tiles. So I have 700ths tiles. So we'll say no to integer chips, but could use tiles. So that's another visual way that isn't integer chips, but is another visual representation. So these are my hundredths tiles. We'll paint them in so that we can identify them between our tens tiles. Our tens tiles are smaller, so we have 4 of those. And then I have, sorry, that's supposed to be a full one. And then I have 8 ones unit. So then students can say, okay, I need to take away 4 ones. So I took away 4 ones. So I only have 4 more ones left. I have to take away 5 tens. Well, 1, 2, 3, 4. I don't have 5, but I can break this one up. 1 tens unit is the same as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I can take away 1 more of those. So that means here I've scrapped this. I can take away 1 more of those. So that means I have taken away my 50 and my 4. So I'm good. I've taken away the right amount. So then I can't count what's remaining. So this was just for our drawing purposes. It's not actually remaining because we took it away. So I have 1, 2, 3, 4, 5, 600 left. And I have 1, 2, 3, 4, 5, 6, 7, 8, 9 tens left, so 90, and I have 4 ones left, so my value is 694. So this method is possible to do visually, but not with the integer chip method, so we're not going to give it a full mark. Let's say it's a 0.5 because it requires more training, more additional support. It can be done visually, but not with this method. So we'll give it a 0.5, but it's a debatable 0.5. And then we go to our negative numbers, and these methods, this is where they shine, is the negative number understanding and comprehension. So -7, take away 4. So now I have -7. And I need to take away 4 positives. Well, and this is important here to note is the terminology. I'm not saying -7, -4. I'm saying -7, take away +4. So I need 4 positives. And again, students can quickly connect that I can add as many 0 pairs as I want, going on forever if they need to. But they would obviously notice that I only need 4, so they probably would have stopped at these 4. So they scrap the 4. And then they count what's remaining. I have zeros remaining, so those we don't even need to worry about. And so I count only my negatives. So I have 7, 8, 9, 10, 11. So my answer is 11, but it is a negative 11 because I have X's left over, or, if it's integer chips, they would be black integer chips left over. So this method works really well. And number 5 is -4 take away a -7. So we start with our -4. I'm taking away, so I have to remove some. I have to take away -7. So if I look at what I have currently, I only have -4 to take away. So I have to add 0 pairs again. And they might write down 7 0 pairs without realizing that they don't need them. That's okay. You'll notice at the beginning, students will write a lot of 0 pairs, and then they start catching on to how many they really need. So I'm -4, 1, 2, 3, 4. I have to take away -7. So now I start taking away 1, 2, 3, 4, 5, 6, 7. I stop here. These zeros I don't really need to worry about because they're all just zeros. So I have 3 positives left over. So -4 minus -7 is equal to 3. So this might be a good way to show students what actually happened here. I had a negative and I took away a negative and I ended up with a positive number. And then if you show them enough examples, you can start rationalizing why a negative times a negative is equal to a positive. They start seeing this pattern that's happening. So through pattern, they learn this rule that we often sort of see as magic. But in this case, we can visually represent it. So there's more of a buy-in. It's less of like, just trust me, I'm your teacher and I'm telling you it's right. So I would say that this method works well. So ultimately, if we're just looking at integers and not worrying about visually, there's 4 that would work. If we're being loose and saying that integers and tiles are sort of our visual representation, then I would say there's 4.5 that would work. I'm going to say 4 out of 5 because it requires an additional method to support it. And all of these, of course, require additional instruction.